Hi everyone, my name is David, I'm a student at Carnegie Mellon, and I'm going to be telling you about some work between me and my co-author Jan Hoffmann that we call Automatic Amortized Resource Analysis with the Quantum Physicist Method. But first, let me make sure I tell you what this work is not about. Despite having quantum in the name, this work does not involve quantum computing, or any actual quantum physics at all. With that out of the way, what this work is about is analyzing programs to determine their resource usage, like how much time, memory, or energy they will take to run. And we want to do this in terms of the size of the program's input. One particular way of performing this kind of analysis is called the Physicist Method, because it metaphorically bookkeeps resources as if they were potential energy. You can imagine storing some amount of potential energy on each piece of an input data structure, like our list here, and paying from that store like a wallet when costly operations are performed. The total amount of energy on the input list would then give a bound on the total resource cost. This not only lets us reason about resources like time, which just monotonically tick down, but also resources like stack, which non-monotonically are allocated and freed, going up and down. The first resource, time, is easily measured with net cost, the change in energy. The second resource, stack, is better described with the high watermark of cost, the maximum amount of resources in use at a given time, which here is simply how much energy we need to start with to not go negative. The goal of the Physicist Method is figuring out how much energy to start with and how much to pay out over time. Right now, let's start by showing how the traditional Physicist Method reasoning works. Here we have a typical length function for a list. If we want to reason about how many call stack frames this might use, then we just need to count the number of recursive calls. In this case, it is easy to see that the number of recursive calls is equal to the length of the input list. Now let's use the Physicist Method to figure this out mechanically by trying to assign some amount of potential per element of the input list. So let's set it up with our input list having 1 unit of energy per element. From here, the manipulations of potential occur in lockstep with our program. When we perform a pattern match, we free 1 unit of energy and keep a tail list with the same energy density as the original input. Then we come to the recursive call. And here, it turns out that we are perfectly set up to pay 1 unit of energy for the call stack frame and provide an argument with the proper energy density for the recursive call. Thus, inductively, we can conclude that the amount of energy we started with, 1 unit per element in the list, is an upper bound on the amount of call stack frames needed, which is exactly the bound we wanted. And this particular example also shows how we can use the Physicist Method in a type system by wrapping the amount of energy into the type of the list, which we do with the yellow superscript here. This also lets us type the function len like this, as taking a list with 1 unit of potential per element and 0 extra units, and returning an integer with 0 extra potential. This type system is called Automatic Amortized Resource Analysis, or AARA, and it can automatically perform the reasoning we just did to find resource bounds by reducing the problem to linear programming. Now, this is great, but there are common patterns where it gets into trouble. Here we see the size function. It is like the length function we just went over, but it gives the number of nodes in a tree instead of a list. If we again want to measure the number of call stack frames needed, the problem becomes a little more complicated. You see, we make 2 recursive calls, and because they occur sequentially, we can reuse the stack from the first call for the second. As a result, the number of stack frames needed is the depth of the input tree, not the number of nodes. However, if one naively uses the Physicist Method, like AARA, one only finds a bound equal to the total number of nodes, given by this function type, with the superscript 1 indicating 1 unit of potential per node in the input tree. There are multiple reasons for this type's poor resource bound. The first is a shortcoming of AARA. Its types do not track leftover potential very well. If you look at the function type, there is nothing to indicate that all input potential is also returned, so there's no way to reason about the reuse of such potential. Now, we do solve this problem in the paper, but this will not be the focus of the talk. The second problem is a shortcoming of the naive usage of the physicist method, which would assign potential locally as a fixed function of each data structure. You see, even if we did solve the first problem and had potential to reuse on the subtree T1, there is no transfer operation to give that potential to the subtree T2. From the time the variable T2 is bound at the pattern match to the time it is given as an argument, T2 is untouched. So neither its type, nor structure, nor anything else about it has a chance to change. The naive physicist method is therefore forced to keep its potential equal to when it was bound, and cannot add in the potential from T1. Now, while this rules out the naive physicist method with locally defined potential, there is still an option for a more sophisticated global approach that takes all data structures as arguments simultaneously, even those that are not being operated on. This is where our work on the quantum physicist method comes in, showing how to derive such a globally defined potential function in a principled, structured way, enough that it can even be automated. And with such a non-local potential function in hand, normal physicist method reasoning can apply. To show the workings of the quantum physicist method, I'm now going to walk through how they work in a setting outside the type system of AARA, so that we don't get too bogged down in notation. Imagine that there are $5, and we give these $5 to Alice and Bob to share. And Alice and Bob are going to go to the candy store and use this money to buy some candy. In particular, let's say that Alice wants to get some Crunch Bars costing $3 for the pack, and Bob wants a Kit Kat costing $2. These costs add up to $5, so it is beginning to look like the way they should split the money should be obvious. Alice gets $3 and Bob gets $2. And this is exactly how the traditional physicist method would reason. That would be the end of the story if not for one more wrinkle. You see, here's the twist. While Bob can just pay for his candy directly, Alice's Crunch Bars are in a vending machine that only takes $5 bills. If we did nail down that Alice gets $3 and Bob gets $2, then Alice could never get her candy because she couldn't use the vending machine. Note that this temporary requirement of $5 is kind of like a potential barrier in physics. Anyway, despite the barrier, there is still a way for Alice and Bob to both get their candy, and it's exactly the way I used to split money with my little brother growing up. We start by having Alice hold all of the $5. She then puts that $5 into the vending machine and buys her candy. She then gets back the $2 in change. This $2 she can then give to Bob, and finally, Bob can buy his candy. What an elegant solution! However, while this solution is very nice for Alice and Bob, it makes our bookkeeping using the physicist method a little harder, and the problem is this step right here, where Alice transfers money to Bob. You see, while the physicist method can do this bookkeeping, it requires an explicit transfer between Alice and Bob to work smoothly. But, as we've already discussed, this isn't really something we want to track. These kinds of transfer operations just do not exist in real code. To deal with this problem, we are going to change how we think about the way that Alice and Bob split their money. Let's look at how they might do it. They could split it $5, $0, Alice could give $3 to Bob, Bob could give $2 back, and so on. Alice and Bob are not adversarial, so they can cooperate and split the money however is most beneficial at any given time. So, rather than fix any one split of the money, we are going to consider a sort of cloud of all the possible splits at once. This is our collection of worldviews, where each worldview tracks a different allocation. By using many worldviews at once, we simultaneously consider whatever relevant ways the money could be split. In one worldview, Alice holds all the money, in one Bob does, and so on. And by representing these many realities simultaneously, this behaves a little like quantum superposition. Now, let's show how this cloud of worldviews enables non-local reasoning in our bookkeeping. This is going to use a principle we call resource tunneling, which builds off of our worldview superposition to get something analogous to quantum tunneling. To do so, we are going to look at these two worldviews in particular, where they split the money $5, $0 between Alice and Bob, and where they split it $3, $2. We are now going to see what happens as we bookkeep our desired solution, where Alice gives Bob the change. The first major principle in this bookkeeping is that every worldview pays the net cost of whatever operations occur. So, when Alice pays into the vending machine, this is the resulting allocation in each worldview. You will now notice that in the second worldview, Alice has negative money. This is usually nonsensical, but we are going to allow it right now, as long as the second principle of this bookkeeping is satisfied. That is, there always exists a worldview that covers the high watermark of resource usage, which would be a worldview where our money never goes negative. You see here, the first worldview satisfies that principle. And now we see the step where Alice gets her change back, still adhering to our two principles. And finally, we see the step where Bob pays. Now, because we've kept to the two principles along the whole way, we can construct a path through our worldviews like this. Notice that this is exactly the same sequence of money allocations as our desired solution. But now the transfer of money between Alice and Bob happens implicitly at the dotted line. There, the transfer is encoded by the path simply jumping to a worldview with a different allocation of money. And each step along the way, we have real, non-negative amounts of money. In fact, no matter the scenario, as long as we follow our two reasoning principles over these worldviews, such a path like this always exists, where money is non-negative and where transfers are encoded implicitly as jumps between differing worldviews. Now, let's go back to our previous code example. By using the updated AARA-style type system in our paper, we can assign the following type. This type differs from the previous in two ways. Firstly, we use a subscript on the tree type to indicate 1 unit of depth potential. And secondly, we include this additional term at the end to indicate how much potential is returned on the input data structure. So, what this type says is that our tree traversal only requires stack equivalent to the depth of the input and gives it all back at the end, which is exactly the bound we wanted to get. And this type is justified by a type system using the quantum physicist method. Just briefly showing some bookkeeping, you can see this spot in the middle, where the circles jump from left to right, implicitly shifting potential from the first subtree to the second, exactly as we needed. Now, in the paper, we go over all the features of the quantum physicist method in detail, like showing how to extract an explicit potential function out of it. We also automate the reasoning using the AARA-style type system, and prove the whole system is sound so you can in fact trust the reasoning going on here. We also apply this type system-based analysis to the OCaml standard library set module, which implements sets using trees. We show experimentally that this can indeed reason better about things like stack and tree depth, allowing for the inference of much tighter call stack bounds than AARA could previously provide, with only moderate overhead. You can see some of the results from our paper here, but to summarize, our implementation never finds worse bounds, and finds strictly better bounds over 30 different functions in the module. And with that, I'll conclude my talk.